Thanks for coming, everybody. So as Neil said, my name is John Hugg. I'm the first engineer at Volt. I'm a disk data store guy, not really a Docker expert yet. And then there's some contact information. If you want to ask me any questions, you can do it after the talk, or feel free to contact me later. So this talk, VoltDB is a distributed system. Docker is really cool infrastructure technology. So we set out at Volt to try to use Docker to improve some of the testing we do. And we're going to talk about that today. And this is not a talk about production deployments with Docker. It's just a talk about testing. I don't have a lot of experience with production deployments with Docker. If you're interested in people who use Volt with Docker in production, I can connect you to the right people. So since we're talking about Docker, I put this slide up pretty early in the presentation. It's certainly relevant, and how sort of it applies to this talk is sort of, we started using Docker, and I'm going to talk about some of the initial successes we had and some of the really cool things we found out that it could do. We wrote an abstract to come here, and we started figuring out all the things it couldn't do. Got a little nervous. Things have gotten better since then, and so that's sort of the shape of this talk here. Is a little bit of what's great, a little bit of what we've ran into trouble with, and then some successes we've had more recently. So very quick, for the purposes of this talk, what's Volt? It's a shared nothing distributed system. It doesn't rely on any other software. It's just a bunch of processes running on different nodes connected to each other. It's a stateful data store, meaning it actually persists information. If you wiped it, you couldn't recreate it because the state would be gone. It's extremely high performance, and it unpacks from a single tarball. So the installation is just move a tarball somewhere, unpack it, and you're ready to go. So broadly, what is VoltDB? Sort of the marketing standpoint, this is the only slide I have on this. I look at VoltDB as the intersection between streaming analytics and ACID transactional state. It's a system that can be both the system of record and the analytics, the streaming analytics system that can allow you to act on that system of record. But like really big and with SQL. All right, moving on. So I've got a few minutes of introduction on Docker. I can't see hands very well, but how many people have done more than kick the tires with Docker? Can people raise hands if you're Docker users? Okay, so like half or so. So bear with me for a few minutes. I'm going to do an intro, and I'm going to cover stuff that's really specific to this talk as well. So the mental model most people have is that Docker is a lot like virtualization, and this is a good place to start in the sense that a Docker container is sort of like your own little OS, sort of like a virtualized image, in that it gives you some isolation. It gives you, you can pick which operating system you want to run. It's based around Linux kernel technology, containers, groups, namespaces, all these things. So it's based on really cool open source stuff. This picture kind of sums up the biggest difference between virtualization and Docker, is that Docker essentially is sharing the kernel between the different guest operating systems, the different containers, whereas in virtualization, the virtual machines are virtualizing their own kernel. And there's some weird para-virtualization and hardware virtualization that kind of enables some sharing between those kernels. But instead of running 3 kernels, you're running 1. So Docker doesn't have to load a Linux kernel per container. Docker also doesn't really have an init system. So you're not really starting the full operating system. You're not booting Red Hat. You're not booting SUSE or Ubuntu. What you're doing is you're just basically starting the file system of those things and running one particular process. And we'll talk about that in a second. But what that means is there's not a lot of other daemons hanging around, not a lot of other processes eating RAM and CPU. So consequently, Docker has very little memory overhead. It starts in like under a second. I can start a new instance, and that really changes how you can use this system. It's very lightweight. If I could run 10 virtual machines on a server, I could run 100 Docker instances, containers. Other things it means that I can't virtualize anything but Linux. So, I can't containerize anything but Linux. In virtualization, I can run Windows, I can run BSD, I can even run Mac OS sometimes. With Docker, I can only run Linux. It's a shared kernel, so if you want a different kernel, you're out of luck. And what that means, even more so than that, is that I can't really fake an entire Linux operating system, right? I've got, in a virtualized environment, I can run any kernel I want, then I can run the CentOS 5.7 with its 2.6.18 kernel, and I can run Ubuntu 15.04 with its, whatever, 5 point whatever kernel. And with Docker, I have the same kernel in both systems. So I can run the CentOS file system and the shared libraries and glibc from CentOS 5.7 and get very different libraries and file system layouts and configuration from Ubuntu, but I'm not really faking that operating system. I don't have any of the supporting daemons that run on those operating systems. The config is very different. It's really just sort of a pretend operating system. In terms of networking, you can really treat these things very similar. The Docker and virtualization have a lot of overlap. They do NAT networking, host networking, where you can sort of take over the host, bridge networking, where you can assign IPs, a lot of the same kind of things that you can do with Vagrant and other virtualization technologies. Docker does something different than most of the virtualization systems with the union file system. So the idea is that if I have, say, an Ubuntu image, and I want to take it and I want to add Java to that, in a virtualization tech, I would take the Ubuntu image, add Java, and save it. With Docker, I take the Ubuntu image, I add Java, and I save the diff of the image. And so I build this onion file system, sort of, sounds like union, where I start with a core, and as I add things, I'm just adding diffs around it. And so when I actually boot this container that has Java 7 and VoltDB, I'm booting the Ubuntu file system plus the diffs, and they're mounted as one image to the container. The way I create Docker images, well, there's more than one way, but the common way is with Docker files. So here's examples of 2 Docker files for this particular onion union thing. I've got Ubuntu 14.04 is the base. The working directory is root. I want to add Java to that, so I use this run command, and that's the thing that's actually going to create another layer. And the default command when I start this image is bash. So if I write docker build, I tag it with Ubuntu JDK, it'll build that image for me and cache it on the system. If I want to add VoltDB, I can say from the Ubuntu JDK system, so building on the image I just built, copy VoltDB from my local file system into that container, into that image, and set the work dir to the VoltDB directory and start with bash. So then I can build that image. I'll call it VoltDB OSCON. One of the important things about Docker is that when it starts up, you get one command. You don't get an it system, like I said, with a set of processes, a set of daemons. You get one command. Now that command could be bin bash, and you could say the default is bin bash in the Docker file. So when I say docker run image name, it's going to start bash. Or I can specify on the command line docker run image name ping VoltDB, for example. And now that container, when it starts up, it's not going to run bash. It's not going to run any other process other than ping. And it's going to run ping at VoltDB and start running. So the command that's in the Docker file is the default, but it can be overridden, and then it's completely ignored. So sort of my onion is getting bigger here now. So what does this look like? Quick demo here. I'm going to start typing, I think. This is all pre-recorded so that for time. But I want to build from this Docker file here my Ubuntu JDK, my Volt image that's based on the Ubuntu JDK image I made. Done. The next step is I'm going to list all the images. So these aren't on the file system. These are in the Docker. I could use the Docker client to list the images that are available. You can see the VoltDB OSCON images available, the Ubuntu JDK, some cached intermediate images. And then I can run this image using Docker run. TI means interactive. RM means throw it away when the process ends. I'm going to use the default bash. You see I can ls, and I'm inside. There's the VoltDB layout inside that image. And I can exit. And that brings me back out to the command line. Running docker run again, I'm overriding the command to run VoltDB. So Volt started. I can hit Control-C. Because VoltDB is the process that I started this with, when I kill VoltDB, I'm back out at the original server. So I can cat the Docker file again because I'm outside. I know the prompts are not particularly clear. Docker also has facilities for getting the logging out of these systems, so it allows you to get the output from the logs from these kind of systems. I'm not kind of going into that today. Also, Docker has volumes. Volumes are the way that it deals with persistent state. so you can mount a volume at a particular place, and if the Docker container goes away, the volume persists, and you can mount that same volume again into another container. Last slide on the intro here, Docker has repositories. So you can basically store your images in your company's Docker repository. You can store your images with Docker the company. They've got this hub thing where you can host any publicly accessible images for free, or you can pay them to host your images. It makes distributing software to a lot of machines on different platforms really easy. This is the computer that I recorded these videos on in my hotel room. One of the consequences of it being not very Mac-friendly is that it was easier just to build bring a high-memory, tiny computer with me to this conference than it was to kind of deal with the Mac. So I've got a video of running VoltDB in Docker with 3 nodes. And, whoops. So here we go. So I'm building that OSCON image again. I'm adding a script called deploy py, which it just makes it easier to deploy 3 nodes. It's not. So I can see that I've got the new image built 4 seconds ago. I've overwrote my VoltDB OSCON image. Now, I'm doing things a little differently this time. I'm giving my container a name. I'm calling it Volt1, V1. I'm giving it a host name. That makes networking a little easier, because what I'm going to do is I'm going to network between these containers. The -P means I'm going to expose 8080 to the host. So if I wanted to open a browser and get to the Volt management console, I could. And I'm going to start VoltDB deploy, this script I wrote with 3 nodes and with double redundancy. So that's the first node. The second node I'm going to do a little bit differently. I'm going to run name v2. Sorry, apologies for watching me type here. Name v2, host name v2, and this link thing is going to say v1 to v1. And what this is going to do is it's going to add an entry to the host for this container, the host file, that's going to have v1, and it's going to point to the IP of the other container named v1. So this is going to allow this container to talk to that container by host name. So my deploy py script that I wrote just connects to v1, and that's how these things connect together. So the last one is going to type almost the same thing as the second one. But essentially what I'm doing here is I'm running on one machine 3 Volt nodes that are all opening lots of ports. They're isolated in their Docker containers. And what I'm going to do after I get this one running is I'm going to kill one of them as soon as they start up and let the other 2 run. So this enables me to do distributed system testing on one machine without worrying about dealing with the overhead of virtualization. So if I have a 16 gig machine, I'm not giving up a bunch of gigabytes to many Linux kernels. I'm not waiting for those things to boot left and right. So here I'm going to kill the second one. And without the... sorry, oh, there we go. So this one killed. These 2 are still working. They have log messages that say that host 1 failed, but they're continuing to process. And there's a video on our website that kind of goes from here and shows you more things that you can do. But I'm going to keep going. So how do we test at VoltDB now that we're sort of done with the Docker intro here? And this is simplified because I don't want to offend all the people who work on our test infrastructure at Volt. There's a lot of engineers who work very hard on this, so if I'm missing a lot of things. But essentially, we divide into unit tests, and I put quotes up there, and systems tests. Unit tests are a mix of unit tests and black box tests. So traditional unit tests, like I take a class or a subsystem, and I fake inputs and outputs, I mock things. There's a lot of that. There's also black box tests, where on a single machine, I may start up a Volt process, run some input, and make sure the output is right. Essentially, these are the tests that I can run on a single machine by checking out our code from GitHub, building it, and running a command to run the tests. It runs lots and lots of small tests in series, and it produces a report, pass-fail, with error messages from any failed tests. It takes over 2 hours to run the current set of VoltDB unit tests on my laptop. There's also system tests. System tests are very different. These are multi-machine tests. These are often long-running tests, not necessarily. We do a lot of fault injections. And we run these not necessarily all the time on every check-in, but usually nightly on the master branch or on any branches that people have asked us to run it on. So our first success is going to be on the unit test side. This is the thing that got us really excited about Docker and kind of the biggest win we've found so far. So running ant check, 2 hours. It's brutal. Nobody does this anymore at Volt. So essentially what we do is we set up this really cool infrastructure, and it's not dissimilar than a lot of places, but we make some code changes, we check it into Git. We've got Jenkins continuous integration in a closet full of servers that notices that you've changed some code. It breaks up that 2-hour unit test into 3 parts, 3 sets of tests. It picks 3 machines that are free in the closet, and it runs them. And then it sends the user a report saying, here's what happened with your check-in, thumbs up, thumbs down. Thumbs up, it goes to, thumbs down, you go back to the cycle of make some changes, commit code to Git, and back and forth. Thumbs up, it goes into the code review process where we'll get some engineers to look at the code. That can be thumbs down, and we go back and make more changes, or it can be thumbs up, and the code is finally merged to the master branch. Depending on which engineer we're talking to, this process either is an average of 2 or 3 cycles to 10 cycles for some engineers. So if the code takes 2 hours of compute time every time you do a check-in, and we're checking in 50, 60 things a day, this is a huge drain on resources for Volt. So it takes just under 1 hour for the turnaround, which also means engineers are sitting around playing ping pong, or they have to multitask and jump between tasks. And that's an hour if the queue is empty. So if all the machines are busy, if for some reason particularly full, then it's even longer than that. A lot of this time is underutilized hardware. So we have tests that do things like test a 30-second timeout. Testing a 30-second timeout is not taxing on a machine. Parallelism is also constrained by a lot of things, but primarily it's network ports. So in terms of, there are places in the test where we assume certain network ports, maybe web ports or other ports, Zookeeper ports that might be the same way. And we've gone through a lot of these tests and made it so that the ports are more fungible. But it's really hard to go through this incredible body of unit tests that we've built over about 7 years and make sure that they all can be run in parallel. Virtualization is one option to get better hardware utilization, but it's kind of a heavyweight solution for this. We've done some of it, but it's tricky because there are times where we want to use the machines we want to use the machines in their entirety. We want to slice up the machines, and certainly we could do that with like Vagrant and certain things, but then it's slower. It's a little bit more heavyweight. Really, Docker sort of came to the rescue and made this a lot better. So the changes we made when we switched this to Docker, we broke up the 2-hour unit test into 6 groups rather than 3. We ran each group in a Docker container, and we ran 3 containers per host concurrently. And this solved all our isolation problems. And we found that with 3 containers, it didn't actually run any slower. Some places maybe run slower, other places probably ran faster because they're testing timeouts and that kind of stuff. In the end, we used 2/3 of the machines, and we used it for half the time. So this is a half the time turnaround back to engineers before we can say thumbs up or thumbs down, and it's 1/3 of the resources, which means you get fewer and fewer times when the queue is full and you have to wait even longer. So this is like 50 times a day we save this resources, which is amazing, and it allows us to buy a lot less hardware, and it wasn't a lot of work. So this is sort of kind of everyone at that company meeting where we showed off this feature. So now we kind of past that success, problems we have with this. So right now in our server closet, we've got machines running OS 10, 10.8, 10.9. Developers love to build Volt apps on their laptops. We've got CentOS in various flavors, all the way back to 5. We've got Ubuntu in different flavors. We've got some other things even in there. We've got different Java versions, 3 different versions. We've got some nodes are running on bare metal, some KVM, some VMware. We've got AWS added into our Jenkins pool quite a bit of the time. Some of them have SSDs, spindles, disk controllers in front of spindles, multiple NICs, NUMA cores. There's kernel settings like is it swap on, transparent huge pages, are those on? The cross product of this is really too big to test. It's enormous. We do our best to kind of test as many combinations of these things as possible. And also, this is certainly the opposite of what we would do in production, right? In production, you pick a hardware, you standardize, you run as few variations as possible, and that significantly reduces your surface area. Because we make a product for other people to consume, we try to test on everything, and we found some really fascinating problems with things because of this. So can Docker and or virtualization help with the variety? What are some of the things we've looked into? And we found basically there's no silver bullet. So because Docker is running the wrong kernel, and because it has no init system, pretending like we're using Docker to test different Linux distributions is really not a complete solution. It doesn't really do a great job at being Red Hat 5 or at being Ubuntu 15. On the other hand, Docker, because there's only one kernel, is very close to bare metal in terms of how you're running. There's not a lot of fakeness between you and the kernel and the hardware. So we like that a lot about it. In terms of the virtualization side, it's very easy to create lots of variety. You can test these different distributions. But we found that sometimes virtualization can hide bugs because the system calls sometimes get slower, and that hides race conditions. Sometimes there's bugs in network drivers that you don't see in virtualization. It's something that we can't virtualize all the things. We still need to run a lot of bare metal for these reasons. Vagrant is a fun thing that we've done some testing. We do some Windows testing on Linux hosts using Vagrant, and it's a neat tool if you're looking for virtualization tooling. So next steps, we get a huge efficiency win. We're working on using it to fuzz Java versions. It might be able to do more, but efficiency alone is still Carlton dancing. So there are a lot of places where we could use Docker in the actual unit tests themselves. I mentioned that there are places where we start up Volt and we do things like we test, what happened in the unit test. We start up two processes locally. We kill one, we rejoin it to test the rejoin process. Maybe we kill both and recover them to test the durability process. We could probably use Docker to simplify that code. Nobody likes that code. It's awful old code. But that would be Linux only, and that's always one of the catches with Docker. So if we're making a distributed system, not sure we want to make our tests Linux only at that level, at the very low level. These tests all run on my Mac today, and it's nice that they can run on my Mac. Another thing is that this was from the abstract. That was another talk at this conference. A Docker image will run exactly the same way no matter where you put them. This is mostly true. If your app cares about the kernel, specifically kernel settings, like, say, transparent huge pages, this leaks through into Docker. It leaks in different ways in virtualization, but it's something where we have found we've been burned by this in a couple of different ways. All right, so we're moving into systems test. Systems test is something that's an ongoing effort at Volt. Can we use Docker in systems tests? We're playing around with this. I've spent kind of some time over the last month working with our test team on this. So we're not done, but here's where we got so far. So the way that system tests have worked since 2009, before Docker existed, we have this is on GitHub. Anybody can go look at this. In VoltDB test apps, we have a set of like 30 or 40 different applications that are all Volt applications of various flavors. Some of them have like ticket names because they're designed to reproduce particular issues. What we do for system tests is we pick one of these. Some of them are pathological. They're designed to be horrible, horrible apps. We pick an OS, a JVM version, hardware config, number of nodes, redundancy level. And we pick a failure profile. Maybe we want the thing, it's just a performance run, so we don't want anything to go wrong. We just want to know how fast it is in the best case. Maybe we want nodes to die and rejoin. Maybe we want the whole cluster to die and recover. Are we testing asynchronous disk persistence? Are we testing synchronous? In one, we've got some tolerance for what recovery looks like. In the other, we don't. Slow disks, other processes, lots of different things. And then we pick a runtime. We run for that amount of time, and we collect any errors or problems and verify that everything's right. We built a lot of infrastructure to do this. It's a huge part of why we trust our system. So let's tear it down. App Runner is the technology we use to run this. It's something that started out as a small Python script, and over time it became bigger and bigger and bigger, and now it does a lot of things. It's based on Paramiko SSH. So it's a Python SSH library. So essentially we've got passwordless SSH between a whole bunch of machines, and we've got Python scripts that goes and does things on those machines. It's very old-fashioned. It deploys a click kit, starts a cluster, sets up an app, and starts clients and creates load. That's the first thing it does. Then it can do any of those fault injection things, like optionally kill and rejoin nodes, kill a whole cluster, inject all kinds of weird failures. Some of them we're going to talk about in a second. It can verify correctness for this, which is very important, and it's by far the hardest thing it does. It can create a report if any of the logs contain anything unexpected, and it can collect logs and artifacts. So when things go wrong, it quickly zooms out, collects all the logs, collects all the snapshot files, the write-ahead log from the database, anything that we might need to debug the problem, and zips it all up for us to debug. So one of the things with this system is that we've got one bare metal or one virtualized host per VoltDB process. So when we pick one of these apps and we say we want 5 nodes, we actually go and get 5 nodes, whether they're from AWS, whether they're from our VMware pool, or whether they're physical nodes. We do that. The first goal with Docker would be nice to be able to run clusters on a single host or on fewer hosts. Specifically, things like we do multi-cluster replication. It'd be nice to have 3 Volt nodes, an entire Volt cluster on one node, on one machine, and then an entire Volt cluster on another machine and network between them. That would make some of our multi-cluster testing a little bit easier. So we'd need to replace SSH commands with Docker. This slide kind of goes through what we need to do. So deployment is just pulling an image. That's great. Works out pretty well. Starting a cluster is just starting containers. We already did that. I've got kind of scripts for that. It's not hard. Killing a node is just stopping the container. Rejoining a node is starting a new container with a different command, but with the same volume. And that's a Docker volume that has all the persistent state. Restarting a cluster is new commands with old volumes. And artifact collection is just, collect up all the Docker volumes. Hopefully all the artifacts are in there. So it's sort of like there's a one-to-one. I could rip out a lot of the SSH stuff, and I could look at some of the Docker stuff. So kind of going all in with this, we still need to use multiple hosts, right? We're not all doing this on the same machine. So we could use SSH with plus Docker. Docker has a bunch of tools that they offer to deal with multiple machines and running them. Kubernetes is certainly a hot technology. All these things make deploying to 100 nodes really easy, but deploying is not the hard part of what we do with AppRunner. That code is written, that code works. Deploying is sort of, for test purposes, is certainly easier than deploying for production purposes. The hardest part is verification under lots of scenarios. So if we have async persistence to a secondary cluster, I need to verify that the data in the second cluster doesn't have to match the data in the primary cluster. It has to trail it within some time bound. And being able to verify that and say, absolutely, this is the correct data within some time bound is where most of the code is in the VoltDB AppRunner system. There is an open question too. I skipped a bullet here. Docker's Linux only, is that a problem? I kind of mentioned before that might be a problem. I think that, if we could support both modes, it certainly wouldn't be a problem. It would be a huge win to be able to say, we can use Docker and when we have Linux and use the old system if we don't, but it kind of means we'd support both nodes. And is Docker different from bare metal testing? My gut feeling is it's close enough for a lot of these, but we've been burned sort of in the past by moving away from bare metal. So this is the pre-conclusion here, which is not the end of the talk. It's sort of a meh. We don't know if we're going to do all this work. We may do some of it. We're going to keep playing with it. And if people are curious, they can email me and I'll keep them posted. So there is something we kind of tried after this, sort of an exploration, Docker for fault injection. So can we build a misbehaving container? One of the things we do with AppRunner right now is we use Linux traffic control. And this thing is awesome. This thing didn't exist when we started doing this work. It exists more recently. And we've switched to it because it's so much easier for us to manage. So if I run traffic control, I have to be root, by the way, but I can say, run this command. Doesn't really matter what the command is, but anything through ETH0, all the packets are going to be delayed by 200 milliseconds. I can also say, well, hey, drop. No, I didn't actually write the same command. Okay, there's a different command. It doesn't matter. If you Google for this, you'll find it. Drop 5% of packets is going to be a different command. Delay with a distribution So I can not just delay by 200 milliseconds, but I could delay by 100 milliseconds as a mean with a 20 millisecond standard deviation. I can do things like, say, the probability I drop a packet based on the probability I drop the previous packet. All kinds of really, really cool ways to make your network bad. So the question we asked is, can we bake bad networking into a Docker image that then we can wrap with a VoltDB to test VoltDB, or you could wrap with Cassandra to test Cassandra, or whatever you want to do. I don't know if anybody knows how to do this. I'll tell you what we've tried. I would love to hear from you. I don't think this is easy to do. So traffic control doesn't persist between boots, which is good, very good. You can always turn off the machine and turn it back on and it works again. But you can't bake it statically into the image. So again, Docker doesn't have like an init system, so there's no way for me to say I can't just add to RC local the traffic control thing. That's something I could do with a virtualized instance or a bare metal instance, or even some of the Docker containers that actually put in their own init system, which seems like it's missing the point. But so I don't know how I can actually make this thing happen every time. So I sort of worked around it with a different solution. We're building a shim layer between the Docker image and the default command. And this is something that seems to be working for us. So what this looks like is, instead of saying Docker run VoltDB, my made bad image, the command, I run Docker run the VoltDB made bad. I add this wrapper command in front of my command. And so the wrapper command basically is the first thing that gets run, does something bad to the network, and then starts the secondary command. This is sort of a weird compromise that seems to work. It's not ideal, but what I can do is I can bake the wrapper commands into my image, so those wrapper commands are easy to distribute. So here's some examples of wrapper commands, and these ones actually have the right TC commands in them, which is good. So Latency Rap is one that I wrote. This is just, naturally it would be more than 3 lines if you were making it flexible and to support different things. But here's a script that if you run the Python, and it could be Bash certainly. It will delay things by 200 milliseconds. Here's a loss wrap where if you put that in front, that Docker image is going to drop 5% of packets. And then here's die wrap. Die wrap is going to start your process and then kill it after 5 seconds. And it's going to exit the Docker image at this point because Docker only runs one thing, and this is the one thing, and when it's done, you're done. So here's a video of sort of trying this out. So what I've got here is my VoltDB bad container, and bad container has those 3 scripts baked into it. So I can make VoltDB OSCON 2 that has VoltDB and the bad container in it. So an example here, I can run, and --rm means go away when it's done. --ti means interactive. I can also run this as a daemon. I get this error here when I try to run this, because what it's trying to do is it's trying to run TC as the default command, and I don't have the right capabilities. So Docker has all this security stuff in it, and you have to add capabilities in order to do things to the original kernel. So in order to use traffic control, I need to have a little bit more kernel privileges. I need to be able to tell the host kernel that my fake eth0 you've built for me, I want to be able to add. So here I've got this command, I'm pinging VoltDB, and I'm pinging it from within the Docker container, and my latency is all at 200 milliseconds higher than it should be. Latency's not very good generally, but it's all more than 200 milliseconds. So that worked. I can exit back out to the host machine. Now let's say I want to start Volt, and here I'll use the command, instead of the one that's baked in the default, I'll add die wrap. So this is going to run the process for 5 seconds and then kill it. There we go, VoltDB create. So starting Volt, and it's not even going to make it all the way to starting here. It's done. And I'm back out to the main, to the outside system here. I'm no longer in the container. The container's done. So this is a little bit of redemption, and this gets us really excited. I can put this bad container into a Docker repository and keep the latest versions of my wrapper scripts there. And then it's very easy to take that Docker image and then push it to all the different places we push things, all the different Linux distributions, the virtualized instances, the Amazon instances. Basically, if they can get to either the Docker Hub, if we pay for that, or our public private repo, then we can do that. I don't even care about making these scripts public. I don't need to hide them. They're all, just test code. It's not Volt code. So that makes it really easy to send to lots of systems. And if you look, we used Puppet for this a lot before we started looking at Docker. And the Puppet, works pretty well. I know they're Portland guys here. But we do have a bunch of stuff in the Puppet repo that says, well, if it's Ubuntu, put it here. If it's Red Hat, put it here. If it's SUSE, put it here. If it's Mac, put it here. And that's really annoying. It's not Puppet's fault, certainly. So another thing here is you don't have any problems with TC settings that won't be undone when the test is over. I'm setting TC on an interface that goes away as soon as the container goes away, instead of setting it on the real interface that the host is using. So that's something where we've had that problem certainly, where you have to kind of reboot a machine if it gets stuck, if you type in something dumb. And certainly there's more than just TC process death. There's tools that will make your fsyncs delay a certain amount of time to your disk. There's tools that do all kinds of horrible fault injection stuff. And the idea of putting those as a wrapper, baking them into the image as files that can be sort of a shell between you and your process that you want to mess with, seems to be something we're really exploring. So this is the end of the talk here. So certainly Docker for managing production environments is very hot technology. If you're testing a distributed system that targets lots of environments like we are, there are different pros and cons. There's certainly a lot of things we like, a lot of things that certainly not Docker's fault, that we wish we could have unicorns and ponies and rainbows made of candy, but the tech is what it is. And also be aware that it's really not, there's a lot of important differences between virtualization and what Docker is doing. So thank you guys very much. There's a microphone up here if anybody wants to ask me any questions or tell me something I didn't know. You also willing to tell me something I didn't know after the fact, because I'm new to this. I've been doing this for a few months now, sort of as a side project. So thank you very much. You've been a great audience.